In this video, we're going to look at two more examples of ideals, which are often called the trivial ideals. I want to start by remembering what the definition of an ideal is. The definition of an ideal is that S is a subring of R, and we call it an ideal if and only if S has these two properties. In particular, what that means is that if we take any element inside R and we take any element inside the subring S, RS and SR both have to belong to the subring. Well, our first example is going to be this. We are going to let S be all of the ring R. So first of all, it's worth noting that S is a subring of R because S equal R is a ring and S is a subset of R, and it's a ring under the same operation, so S is indeed a subring. The other thing that's worth noting is that if I pick any element inside the ring R and I pick any element inside S which just happens to be equal to R, then of course R times S is going to be inside R, but R and S are the same set, and S times R is going to be inside R, but R and S are the same set, and that's enough to say that RS is inside S and SR is inside S, and so S is an ideal. This may seem like a silly kind of an example. It is worth pointing out that what we're using here is closure of times on ring R to make this particular example work. But the upshot is that every ring R is an ideal of itself. And let me clean that little guy up to make it more readable. So every ring is an ideal of itself. Okay, our second example is going to be this. We're going to let S be the set containing just the zero element of ring R. And it turns out that this set is also an ideal. So I want to show S is an ideal of ring R. Well, the first thing that I need to do is I need to show that S is a subring, and then I also need to worry about showing that it is an ideal. So let's see. First show. So I want to first show that S is a subring of R, and I'm going to use the subring criteria. So let's see. First of all, I need to show that S is not the empty set. Well, the zero element belongs to S, so S is not empty. The next thing is I need to show that for any pair of elements inside S, A minus B belongs to S. So I'm going to let A and B be inside S. But remember, S consists of only one element, the zero element. So that tells me that A is equal to 0 and B is also equal to 0. Hence, A minus B is just 0 minus 0, which is equal to 0 in any ring, and hence A minus B belongs to my set S. And then the final thing for showing that this weird set is indeed a subring is that, again, for every pair of elements inside the set S, I need to show that A times B is inside S. Well, again, I let A and B be inside my set S, which is equal to just the zero element, the set containing just the zero element. So that tells me A is equal to 0 and B is equal to 0. Well, let's see. That's going to tell me that we have A times B being 0 times 0, but 0 times 0 is just 0, and that does belong to S, and consequently, our set S, which consists of the set containing just the 0 element, is indeed a subring of ring R. Now we still have to show that it is an ideal. So, is this set an ideal of R? Well, to show that it's an ideal, we have to let R be any arbitrary element in our capital R, our full ring, and we need to let let's call it A be any element inside the subring that consists of the 0 element and nothing else. And we need to show that R times A and A times R both belong to the subring, and I need to make that notation correct. So we need to make both RA and AR belong to the subring consisting of just the 0 element. Well, look at this. RA is just R times 0, and we know that anything times 0 is equal to the 0 element. So RA does indeed belong to my subring. And likewise, AR is equal to 0 times R, and 0 times anything is also equal to the 0 element. So A times R is indeed inside my subring. And these two facts together say that the subring is, in fact, an ideal. Well, what this means is that every ring now, so every ring R contains two ideals. Namely, the subring consisting of just the 0 element and the full ring itself. And these two ideals are usually called the trivial ideals of R. And they are very similar to the trivial subsets of a set. So let's just recall some language from if A is a set, the trivial subsets of A are the empty set and A itself. So trivial ideal is mimicking the language of trivial subset. It's just that the smallest ideal is going to be the ideal containing the 0 element inside the ring. And I'll end this particular video with a question. So here is a question to think about. When does a ring have non-trivial ideals, and when does a ring have no non-trivial ideals?